the area between curves. Let's find the area bounded by the graphs of f of x and g of x as shown. Notice in this case, when we're finding an area, we're talking about a physical area, not an integral area. So the area is going to be strictly positive, or at least non-negative. Now, even though we're not finding an integral area, quote unquote, we will use integrals to find the area. How do we do that? We'll do it in a very similar fashion that we did when we found areas under one curve. That is, let's draw some rectangles. I'll draw one representative rectangle whose base is delta x, because the area of any rectangle is height times base. In this case, height times delta x. The only thing we're missing is the height. I highly recommend that you draw these heights, and then we get to volumes, draw radii and other things, so that we can find the length. And the length of something is always big minus small. So in this case, the height is the big y value, f of x, minus a smaller y value, g of x. So to find the area, we're going to shrink our rectangle size down to 0. We're going to sum all these really small rectangles together, whose height is f of x minus g of x, and whose base is dx. Now, where do we start making these rectangles? Way over here at x equals a, the first intersection point. Where do we stop making the rectangles? Way over at x equals b, the other intersection point. What if we had a more complicated looking graph like this? What is the area bounded by f and g? Once again, I can make some representative rectangles. I'll make one over here, and I'll make one in the other part. And I see that the area of the rectangle in the first part is height, that is big y value minus small y value, times its base. The area of the rectangle on this other side is height. In this case, g is the big y value, and f is the smaller y value. So the height is g minus f, but the base is still dx. And to find the area, I'm going to sum up all the small rectangles on the first part, from x equals a to x equals b, plus add all the rectangles on the right part, starting at x equals b and going to x equals c. Now, we could also do the following. We could have a shape like this and to find the area. Now, you might think, let's do the same thing we've been doing like that, kind of get a dx and finding rectangles, but that's a pretty hard thing to do. It's much easier if we go this way, and we draw our rectangles left to right or right to left. And now the width, or the base of a rectangle, is dy. So a quick note, if the width of your rectangle or shape is dx, then everything should be x's, including your limits. But if the width of your shape or base or whatever we call it is dy, then everything should be in terms of y's. So I have the base. Now what's the height? The height is the big value. How do I know this is the big value? Because it's the bigger x, right? X's get bigger as we go to the right. So the big x value is f of y in this case. The smaller x value is g of y. And so the length of anything is big minus small. And then to find the area, we're going to add all of these really small rectangles together, starting where? Well, down at this lower intersection point, y equals a, and stopping, as I keep making rectangles, but I stop way up here at the top intersection point, y equals b. Let's do a couple of really simple examples. Let's find the area bounded by one region of sine x and cosine of x. I have a representative rectangle here, and we're trying to find the shaded area. So the area is what? It's a summation of really small rectangles. My width is dx, so everything will be in terms of x. What is the height? Well, it's the big Y value, given by sine of x, minus the smaller y value, given by cosine of x. From where to where? Well, we'll start here at this intersection point. So where does sine of x equal cosine of x? Well, the smallest positive value is pi over 4. So that'll be our lower limit. And then the next time cosine and sine are equal is at 5 pi over 4. So at x equals pi over 4, both of these values are root 2 over 2. And at 5 pi over 4, both of the values, that is sine and cosine, are going to be negative root 2 over 2. So now let's find some antiderivatives. The antiderivative of positive sine is negative cosine. The antiderivative of negative cosine is negative sine x. From pi over 4 to 5 pi over 4. I'm going to make this problem a little bit simpler for myself by factoring out the negative 1, giving me negative cosine plus sine. From pi over 4 to 5 pi over 4. I will leave the negative alone for a little bit. And now I'm going to plug in what? Well, let's plug in 5 pi over 4, my top limit, giving me cosine of 5 pi over 4, negative root 2 over 2, plus sine of 5 pi over 4, so another negative root 2 over 2, minus, now let's plug in our lower limit, cosine of pi over 4 is root 2 over 2, plus sine of pi over 4 is also positive root 2 over 2. And then we get what? Well, I get negative, and the first part here we get negative 2 root 2 over 2. And back here we get minus another 2 root 2 over 2. And if I change all my signs, we end up with positive 2 root 2. So that is the area between one section of sine and cosine. One more example, but let's do everything in terms of y. So I'm going to build my rectangles. I'll draw one represented one that I know I start down here, I end up here. Each width is dy, so I know that everything should be in terms of y's. What is the height, that is the big value of my rectangle? So it's my bigger x is 3 minus y squared, and then the smaller x value is 2y, so we get the height by doing big minus small like always. The only thing we're missing are our limits, which are going to be the intersection points of these two graphs. So we can set them equal to each other. 2y equals 3 minus y squared. Y squared plus 2y minus 3 equals 0. And I'll factor again over here, giving us y plus 3 times y minus 1. Meaning my lower limit, the smaller y value, is negative 3. My upper limit, the higher y value, is positive 1. We can integrate now, giving us 3y minus y cubed over 3 minus y squared from negative 3 to 1. Plug in the upper limit, we get 3 minus a third minus 1 minus, let's plug in the lower limit, we get negative 9, and then let me do this over here separately, we get negative 3 cubed over 3. That'll simplify to positive 9. And then minus negative 3 quantity squared gives us another 9. Let's simplify this down a bit. Those will cancel. In the front part we get 2 minus a third. In the back part we get plus 9, giving us 11 minus 1/3, or 32 thirds, which is the area of the shader region bounded by those two graphs.